Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to continue our series on titration problems. The previous video was on strong acids, strong bases. This video is going to be on weak acids and strong bases. So if you haven't watched that previous video, I do encourage you to watch that one, probably before watching this one. Okay. So how is this problem set up? Okay. Well, we're going to take a beaker that has 50 milliliters of 0.3 molar acetic acid, which is a weak acid, okay? And we're going to open up this burette and we're going to pour in some sodium hydroxide and calculate the pH at different amounts of sodium hydrox being added. Now, the first problem is before any sodium hydroxide's been added. So at 0 milliliters, okay, what's the pH inside this beaker even before we begin? Well, as long as we have the molarity and the Ka value, we can calculate the pH. So we come over here to our equation, which is acetic acid with water to make hydronium and acetate ions. We're going to plug in that 0.3 molar concentration, and then what we're going to do is we're going to use the Ka value to figure out the hydronium ions at equilibrium. So remember, water is not included in the equilibrium expression. So this is going to shift to the right, so it's going to be minus x. And as it shifts to the right, we're going to produce some hydronium and some acetate ions. So this is going to be 0.3 minus x. This is going to be x. This is going to be x. And Ka, which is equal to 1.8 times 10 to the negative 5, is equal to the products, which is going to be x squared, over the reactants, and we are going to approximate this as 0.3 because we think this shift is going to be small because the equilibrium constant is small. And all of this is going to be equal to that number, 1.8 times 10 to the negative 5. When we cross multiply and we solve for x, we find out that x is going to be equal to 0.00232, and if we're trying to calculate the pH, it's simply the negative log of the concentration of hydronium ions, and this x value is the concentration of hydronium ions. So we plug it in, and we find out that we get a pH that's equal to 2.63 for our first problem. So before any base was added, the pH is at 2.63, which sounds like an appropriate pH for a weak acid, okay? Second problem is when we add 25 milliliters of acid. Now, 25 milliliters is considered the half equivalent point because if these concentrations are the same, and I have a volume of 50 here, then it would take 50 milliliters to get to the equivalent point. So half of that is 25, and we call that the half equivalent point. And that point is going to end up being pretty important for us in this series of questions, okay? So the first thing that we need to do is we need to use this BCA, but everything in here has to be in the unit of moles. And right now I have molarity and volume, and I'm going to use those molarity and volumes to calculate the moles. Remember, all I'm doing is using the molarity equation here, and I'm cross-multiplying and finding out that moles is equal to molarity times volume. So I'm going to take the molarity and the volume of the acid, which is going to be 0.3 for the molarity, and that's moles per liter, times the volume of 0.50 liters. The liters cancel out, and I'm left with 0.015 moles of the acetic acid. I'm going to do the same thing for the base, molarity times volume. The molarity is still 0.3 because the molarity for both of them are exactly the same. But this question is asking about 25 milliliters. So that's the question that we're on. So I'm going to multiply that by 0.025 liters. Liters cancels out, okay? And this comes out to be 0.0075 moles. So I'm going to put that 0.0075 moles in for the sodium hydroxide. In fact, everything is in here in moles, so I'll just kind of take that out, okay? So in a multimole conversion that's 1-to-1, well, whichever one's the lowest is what we'd call the limiting reactant. So I know all of the sodium hydroxide is going to react, and if I know that if 0.0075 moles of sodium hydroxide reacts, because of the 1-to-1 ratio, it's going to be the same amount for the acetic acid. So half of it reacts of the 0.015. So if I subtract these numbers, the other half is still remaining unreacted. Okay. Now remember, if these things react, then I'm also going to produce products. Okay. And if I start with nothing and I increase it by 0.0075, then this is the amount of moles of water and sodium acetate that I have. Okay. Now, this is how the problem starts to change from our previous video series. Okay. And that is dealing with the salt that's created over here. Okay. In the previous video, the sodium ions and the chloride ions, okay, were both negligible, but I don't have sodium chloride here because I have a weak acid. So this weak acid reacting with a strong base is going to make water, okay, and then this salt that's made up of sodium ions and acetate ions. These sodium ions are the conjugate of a strong base, which means it's a negligible acid. However, the acetate ion is the conjugate base of this weak acid. If you have a weak acid, its conjugate is going to be weak. So we are very concerned about the acetate ions that are being produced, okay, in this reaction because it has an effect on pH. Where the strong acid, strong base problem that we had, the salt had no effect. Okay, so that's the difference between the two videos that I've made on titrations. Okay, so when you're done with the BCA and having the whole reaction react, you have to do some investigating. The first thing that you're going to look for is strong stuff. If no strong stuff is present, you look for weak stuff. And if no weak stuff is present, then the pH is probably going to be 7. Okay, so let's go ahead and do that. Is there any strong stuff? The answer is no. All of the strong base is completely gone. Okay, but there is weak stuff. There's weak stuff with the acetic acid, okay, and then there's weak stuff here with the sodium acetate, which is going to split up and form acetate ions, which ends up being very, very important. Okay, so I know these are the two things that affect pH, and we don't want them in moles anymore. Okay, we want them back into molarity. So we put them into moles so that they can chemically react, but when they're done chemically reacting, mole unit isn't very helpful to us, so we're going to put it in molarity units. So I'm going to go put this back into molarity. We're going to take these moles, 0.0075 moles, and we're going to divide it by the volume. Now remember, we mixed 25 with 50, so that's 75 milliliters or 0.075 liters, and that comes out to 1 molar of the acetic acid. Well, this number is the same thing, so we're just going to take that 0.0075 and divide it by 0.075. This is also 1 molar as well. Okay. Now remember, this sodium acetate that's right here, okay, it's going to split up into its ions. So it's going to go through this kind of process, and I don't really care about the sodium ions. What I really care about are these acetate ions. So if I do a BCA here and I plug in 0.1, that's going to be all gone. But really, it's going to be the acetate ions that I really, really care about. Okay, so we're going to plug in the 0.1 molar acetic acid. We're going to put that number in right here. Okay, and this 0.1 molar of the acetate ion, that's going to go right in here. So we end up finding out that this is actually a buffered solution because its acid and its conjugate base are present at the same time. So let's go back into this ice chart and do some erasing. And let's go ahead and plug in these values of 0.1 for the acetic acid and 0.1 for the acetate ion. And this is minus x, this is plus x, 0.1 minus x, and 0.1 plus x. This is approximately 0.1, and this is approximately 0.1 as far as the setup. Ka is going to be equal to x times 0.1 divided by 0.1, and that's going to be equal to the K value of 1.8 times 10 to the negative 5. And what you're going to see, okay, at the half equivalent point, when half of it reacts and half of it doesn't, your molarities of your acid and your conjugate base, they're going to be the same. And when you put it into the equilibrium expression, you're going to find out that they cancel out, okay? So X, which is equal to hydronium, is simply equal to your Ka value, and that's where we say pH is going to be equal to pKa. So all I have to do is take the negative log of the equilibrium constant to get the pH, and we end up finding that the negative log, okay, of 1.8 times 10 to the negative 5 gives us a pH of 4.74. So 4.74, and off to the side, I'm just going to put in here, pH is equal to pKa at the half equivalent point. That's what's so important about the half equivalent point, okay? So that's how you do this problem. The next problem is just kind of like the same process, okay? However, we're going to put in 48, okay? Now, these last two problems are going to be different, okay? So let's just kind of practice this problem. So I'd like you to pause the video, okay? And I'd like you to put, try to work this problem out on your own where you put in 48 milliliters instead of 25. And when you come back, I'll be working on the problem and we'll see if you did it the right way, okay? So here we go, okay? So the way this problem is switching, okay, is that we're putting 48 in here instead of 25, okay? And when you do that, you're going to find out that the moles is 0.0144. So I'm going to come up here to my BCA and do some erasing. And I'm going to put in 0.0144 right here. Now, this is still the limiting reactant. All of it's going to go away. There's not going to be anything left. And there's only going to be a very little bit of acetic acid remaining. Now, remember, we are also going to produce 0.0144 of both of these items. And one of them is important, and that's going to be the sodium acetate, because remember, the sodium acetate is going to split up into its sodium ions and acetate ions, okay? So the two things that are going to affect the pH is going to be the weak acid, okay, and the sodium acetate, because there's nothing strong present. So if there's nothing strong, we look for the weak stuff, okay? So we're going to figure out the molarity. So we're going to take the moles and divide it by the volume. So 0.0006 divided by the volume, and 48 and 50 is 98, or 0.098. And we're going to figure out that the molarity here is, when you do that, is going to be 0.0061. And then we're going to do the same thing here. We're going to take the moles of 0.0144 divided by 0.098 liters, and we find out that the molarity here is going to be equal to, okay, get the right notes here, okay, that molarity is going to be equal to 0.147. So what you're going to see as we get close to the equivalent point, all of this is being consumed, okay, a good portion of it at least, and we're producing more of this conjugate base, sodium acetate. And remember, if we come in here and we put in 0.147, then we're going to have 0.147 of the acetate ion. So how does that change the equation over here? Instead of 0.1 for each of them, this time the molarity for the acetic acid is only 0.0061, where the molarity for the acetate ion is now 0.147. It's much greater. These ratios are no longer equal to each other. It's really starting to push towards the acetate ion, okay? So let's go ahead and do our minus x and our plus x's, right? So we're still going to approximate this. because this value is small, and I think the shift is going to be even smaller. So this is going to end up being x, and this is 0.147 plus x, which is approximately 0.147, so approximating both of them. The Ka is going to be equal to x times 0.147 divided by this small number, 0.0061, and that's equal to 1.8 times 10 to the negative 5. Cross multiply, solve for x, and this x is going to be very, very small, okay? It's only 7.47 times 10 to the negative 7. So this shift to the right, super small because of the common ion effect. There's so much molarity over here that this shift is going to be really, really small. And this is going to be the concentration of the hydronium ions. So the negative log of 7.47 times 10 to the negative 7 is going to give you the pH of 6.13. So I'm going to come back over here and put the pH of 6.13. Now we only have 2 problems left, okay? This next problem, though, I think is the hardest question for students, okay? So I'm going to start as the equivalent point of a weak acid, strong base. So let's get right into this problem, and let's work this one out together, okay? So let me do some erasing on the board. Let me remove this stuff, okay? And what we're going to do is we're going to change that to 50 milliliters. This is the equivalent point. And when you're at the equivalent point, you're going to find out that your moles of acid and your moles of base are exactly the same. So 0.015 and 0.015 for our starting amounts. They are all going to react. There's no limiting reactant here or reactant in excess. They both react completely, and there's no reactants left over whatsoever. So nothing here and nothing here. So no weak acid, no strong base, but we're going to produce some water, and we're going to produce some sodium acetate, okay? Now remember that sodium acetate is going to split up into its ions, so I'm going to come in here and put 0.15. Oh, I'm sorry, I actually have to get the molarity first, so let me do that. Moles over volume. The moles are 0.015, okay, over 50 and 50, okay, which is 100. So that's going to be 0.100, and that's how I got that 0.15. So I was just getting ahead of myself a little bit. So this is going to be all gone, and I'm going to be left with just 0.15 molarity of acetate ions. Now, I know acetate ions are a weak base, and over here I have an acid equation. So if I have it, that won't work, right? Okay, you can't use an acid equation if the only thing that's present is base. So for this problem, at the equivalent point, I need to come in here and write a base equation. And if I have a base equation, I can't have Ka either. If I have a base equation, I have to use Kb, not Ka. So I will use Ka, though, to calculate the Kb. So let's get a base equation written in here. And the base equation that we're going to write is for the acetate ion. So the acetate ion plus water, if it's acting like a base, it's going to accept the proton to form acetic acid and hydroxide. And I'm going to plug in this 0.15 right here. Now, the only thing that I need now is a base K value, but all I have is an acid Ka value, and this is where we have to remember that Ka times Kb equals Kw. So if I want Kb, I'm going to have to divide by Ka on both sides. Kw is 1 times 10 to the negative 14. Ka is equal to 1.8 times 10 to the negative 5, okay? And if you work that out, you're going to find out that Kb is going to be equal to 5.56 times 10 to the negative 10, okay? Now I can complete the problem now that I have a base equation and an equilibrium constant that is basic as well. So this is going to go down x, this is going to go up x, 0.15 minus x is approximately 0.15 x and x. And KB is equal to the products, x squared, over the reactants, 0.15, and that's equal to my new number of 5.56 times 10 to the negative 10. Now, I'm going to do some cross multiplication here, and I'm going to solve for x. X is equal to 9.13 times 10 to the negative 6. And if I take the negative log of this, okay, remember, X is equal to hydroxide ions. So if I take the negative log of that, I'm going to get POH. And the negative log of 9.13 times 10 to the negative 6 is going to give me a POH of 5.04, which is going to give me a pH of 8.96. So 14 minus 5.04 is going to give me 8.96. So once again, this is the hardest problem of this series because we switched from having an acid equation, because before we had excess acid, okay, and we switched it over to a base equation because the only thing that's present is that conjugate base at the equivalent point, because all of the reactants are completely consumed and all we have left is this salt that consists of a conjugate base, okay? And that's why we had to write the base equation and then come up with AKB, okay? Now, the last problem is actually the easiest of all the problems that we've done before, but a lot of times students make this problem a little bit more complicated than what it needs to be. So let's take a look at 52 milliliters. So I'm going to come in here, I'm going to do some erasing, and we're going to do 52 milliliters. So if we come in here and change this from 50 to 52, 0.3 times 0.052 is going to be 0.056. So my acid is still 0.015, but now my base is a little bit more at 0.0156, okay? So right now, okay, the acid is now the limiting reactant because we have a smaller amount of acid. In the previous problem, they were the same. In the problem before that, the base was the lower one, okay? But now the acid is the lower one. So it gets completely consumed. There is no longer any weak acid present, okay? Now, if I know 0.015 of the acid reacts, then because of the 1-to-1 ratio, the same amount of sodium hydroxide reacts, which is going to leave me with a little bit of strong base. Now remember, that's also going to produce some water, and it's also going to produce some sodium acetate. So we still have these moles of water and sodium acetate, okay? Now remember, when we're calculating pH, okay, and this is what makes this problem the easiest one, when you're calculating pH, you always look for strong stuff first, okay? And if there's no strong stuff, then you look for weak stuff. And if there's no strong stuff or weak stuff, it's just a pH is going to be water of 7, okay? In this problem, we actually have strong stuff present. This is the only thing that we need to look at, okay? And if only that strong stuff is present, there's no more equilibrium problem, okay? Because strong bases are not in equilibrium. Now, we still have to calculate its molarity, so let's go ahead and calculate the molarity. The moles is 0.006, and it's all going to be over, so 52 milliliters plus 50 is 102 milliliters, or 0.102 liters. And when we calculate that, that should come out to be 0.00588 as far as the molarity of the sodium hydroxide, okay? And this is the only thing that I have to be worried about. I don't have to be worried about this weak base because I have strong base present. So strong stuff first, okay? And that's kind of like our priority, okay? So if we have a strong base present, we don't have to write a weak base equation. We need to write a strong base equation. So let me do some erasing over here and write a strong base equation. It's going to ionize 100%. So whatever I have over here, as the molarity of the strong base, 0.00588, okay, all of it's going to go away. All of it's going to react. It's going to push completely to the right-hand side. There's not going to be any sodium hydroxide left over. It's all going to be sodium ions, which have no effect on pH, but it's also going to create the hydroxide ions, and this is the piece that I'm interested in. If I have the molarity of hydroxide ions, I could take the negative log of that, and that will tell me the pOH, because the pOH is the negative log of the concentration of hydroxide ions. So if I plug that in here, I will figure out that the pOH is equal to 2.23. And from that, I can calculate the pH by doing 14 minus 2.23, and I get a pH of 11.77. So the last problem, 11.77, doesn't have any equilibrium in it because it's a strong base, okay? And if strong base is present, we're going to concentrate on the strong base in order to calculate the pH. So after doing all of this, these are the values of pH for these different volumes of sodium hydroxide. I hope you found this content helpful, and if you did, please give it a like and subscribe. When you add that comment, it really does push this information out to other students that are interested in learning chemistry.